Hey everyone, and welcome to today's Explainer. If you've ever felt like your app is just dragging its feet, or maybe you just really want to understand the actual anatomy of a highly efficient system, you're in the right place. Today, we're unpacking a structural map derived straight from our source material that completely breaks down performance optimization. It's essentially a highly logical, precise architectural tree, and honestly, it's just a fantastic toolkit for rethinking how we view and ultimately manage app performance. To navigate all this, we're going to follow 5 main branches today. First, the optimization landscape. Second, memorization and its hooks. Third, the power of virtualization. Fourth, bundle optimization and lazy loading. And finally, we'll wrap up with profiling the final results. Let's get right into it. Section 1, the optimization landscape, the foundational map. So our source material presents performance optimization not just as some random grab bag of cool tricks, but as a very clearly defined hierarchy. Just look at these nodes. We start right at the top with memorization, move down through virtualization, into bundle optimization, lazy loading, and finally land on profiling. These are the distinct branches of our optimization tree. So when you're staring down a sluggish interface, you really don't need to just guess what to fix. You consult this hierarchy starting with memory management all the way down to your final diagnostics, and you pick the exact right tool for the job. Moving on to Section 2, memorization and its hooks, the memory hierarchy. Right? So before we even think about looking at how things are rendering on screen or how files are flying over a network, we really have to look at memory. Basically, memorization is a technique to optimize performance by storing and recalling previously computed results. Think of it kind of like a super intelligent assistant, a system that remembers the heavy lifting you did in the past, so you literally never have to repeat it. If an expensive calculation's dependencies haven't changed, or if referential equality is maintained, this system just hands you the saved answer instead of spinning up the CPU all over again. It saves you future effort. And look, in the world of computing, saving effort means saving time. And this part of the map breaks down into 3 very specific sub-branches. First, we have useMemo, which is fully dedicated to caching values. Then we have useCallback, which is specifically for caching functions. And finally, React.memo, designed for caching entire components. Just notice how incredibly logical this layout is. Depending on what exactly is bogging down your application, maybe it's a super heavy math value, a function that keeps getting recreated, or a component that's just needlessly re-rendering, you simply navigate to the precise subbranch you need. The big takeaway here is that memoization isn't a blunt instrument, it's a surgical one. Look, we've all accidentally frozen a browser with an infinite re-render loop at some point, right? But by utilizing useMemo, useCallback, and React.memo correctly, you are actively managing your application's memory hierarchy. That means no computational energy, and frankly, no developer sanity, is ever wasted. You're just retrieving what you already know. But hold on, let's pause here and ask a pretty critical question. We've mastered memory at the micro level with these hooks, but what about rendering massive amounts of data? Like, what actually happens when your memory is perfectly managed, but you still have 10,000 items trying to squeeze onto the screen all at the exact same time? How do we handle that kind of UI rendering without just completely freezing the interface? Which brings us to Section 3, the power of virtualization, handling the UI. Okay, so we've moved away from the memory subbranches, and now we're looking at a standalone tactic strictly dedicated to the user interface. Virtualization is basically the strategy of rendering only the items currently visible on the user's screen. Imagine a massive, endless list as a giant roll of film. Well, virtualization is the projector that only shines light on the single frame currently sitting in front of the lens. Instead of totally overwhelming the browser with thousands of hidden DOM nodes, it dynamically creates and destroys them right as the user scrolls. And this is exactly how you achieve that buttery smooth, ultra-responsive interface, honestly, no matter how massive the underlying dataset actually is. Awesome! So our data is cached, our DOM nodes are virtualized, and we're scrolling smoothly. But here is another vital question for us. What about the initial load? Because let's be real, smooth scrolling doesn't mean a thing if the application takes 10 whole seconds just to show up on the screen in the first place. That brings us perfectly to Section 4, bundle optimization and lazy loading, delivering assets efficiently. Let's put these 2 distinct but super closely related tools side by side to really understand them. On the left, we've got bundle optimization. This is all about shrinking the total package size. It's removing the excess weight so your users aren't downloading half the internet just to view your landing page. Then, on the right, we have lazy loading. This defers the delivery of non-critical parts. It's basically deciding that you don't need to pack absolutely everything for the very first day of the trip. So one makes the payload smaller, while the other delays sending the parts you simply don't need immediately. I like to think of them as this really powerful, sequential 1-2 punch for getting your code to the user as rapidly as humanly possible. Step 1. Bundle optimization. You minify, you compress, you ruthlessly eliminate dead code, stripping the whole package down to its absolute leanest form. Step 2. Lazy loading. You take that super lean package, chop it up, and send over only the most critical pieces needed to render that initial screen. Meanwhile, the rest of it just loads quietly in the background when requested. By following this exact sequence from our optimization tree, your initial load times are going to drop dramatically. And finally, Section 5. Profiling the final results, the diagnostic check. There's an old saying, you cannot manage what you do not measure, and that's absolutely true here. Profiling is measuring performance to identify bottlenecks and verify your optimizations. This is the crucial concluding step of the whole map. I mean, you've implemented memoization to save memory, you've used virtualization to smooth out the UI, and you've aggressively optimized and lazy loaded your bundles. But did it actually work? Well, tools like the React Profiler or Lighthouse shine a spotlight on exactly how many milliseconds every single operation is taking. That allows you to definitively prove that your architectural choices were actually the right ones. So, we've reached the end of the optimization map. We've gone all the way from memory hooks right down to profiling, which really leaves me with one final thought for you to ponder. You now have the complete architectural tree. You know exactly where to find use memo, virtualization, and lazy loading. You have the entire toolkit. But when you take this map and apply it to your own projects, what will your profile reveal? Will it show a flawlessly optimized machine? Or is it going to uncover some bottlenecks you never even knew existed? The map is yours to use. Get out there and start optimizing.